see the screen?
Yes, yes, we can see the screen.
Yeah, thank you very much. So I am just continuing from where I left yesterday. So I have kept a few things written over here, and they're mostly topological stuffs. And let's see. So we know what is meant by a function being continuous at a point and a function being continuous in a space. So if we have a pair of continuous functions, f and g, they're defined suitably so that their composition is defined, then their composition is also continuous. That is one thing. So someone is not muted. Can everybody please mute yourself? Yeah. So if two functions f and g are continuous, then so is their composition g composed f. So we know this from our basic knowledge, but this is indeed true for any topological spaces. Okay, and if we take the restriction of a function that is continuous, if we take the restriction to a subspace, then it is again continuous. So if we talk about continuity of this restriction, you just look at the cursor, then we consider A with its subspace topology tau A, okay, that it obtains from its mother space X. Okay, so once again, these are topological facts, and one can prove them very easily. So I'm not going to give a detailed proof of any of these results, but one can prove this, and I request you guys to prove them because they are easy. So as I said, we know about a function being continuous on a space in terms of inverse image of open sets is open. But this theorem, it gives a refinement of this result. It states that it suffices if you have inverse image of basic open sets is open. Okay, given any basis on the right hand side, meaning any basis of y, if inverse u is open on the left hand side, meaning the inverse image of any basic open set is open, then it's called a continuous function. One can prove this easily. This is an if and only if condition. So you just spare a few lines and prove it. And also, a function is continuous at a point p belongs to S if and only if given any basic open set on the right hand side, say U that contains fp, you have a basic open set on the left hand side as well that contains p, such that f of w is contained in U. So whatever we know about continuity in terms of open sets, okay, they are actually true for basic open sets. Okay, but always remember this. This is very useful. So a function between two topological spaces is called a homeomorphism if it is bijective, continuous, and whenever it is bijective, you can talk about its inverse function, f inverse. So if it is bijective, continuous, and f inverse is also continuous from y to x. So if these three conditions are satisfied, bijective, continuous, and f inverse is continuous, then we call this map to be a homeomorphism. It's needless to say that if f is a homeomorphism from x to y, then f inverse is a homeomorphism from y to x. One can easily see that. And if there are two spaces x and y, and if there is a homeomorphism between x and y, we say that these two spaces are homeomorphic or they are topologically equivalent. So if you just look at this map from R2 to C, that x, y, this pair, it goes to x plus iy, you can verify that this is a homeomorphism. If I talk about a map, then they are topological spaces. So since nothing is mentioned, we just make a habit from now onward. If nothing is mentioned in the Euclidean spaces like R2 or Rn or C, okay, we will assume without laws of generality, that they are equipped with the Euclidean topology. Like here, this R2 is equipped with the Euclidean topology, and on the right hand side, C is equipped with its Euclidean topology. And this Euclidean topology of what, we will discuss in detail just in few seconds. Nevertheless, we just remember this fact that R2 and C, they are actually homeomorphic with each other. So topologically, there is no difference between these two sets, okay, these two spaces. And what is neighborhood of a point? We all have heard about this term neighborhood of a point, but in general, for a topological space, if a point belongs to a topological space, then a set A is said to be a neighborhood of X if between A and X you have an open set. This is what is called a neighborhood of a point X. First of all, this A should contain X, that is obvious from this relation, and between X and A you have an open set. So this is what is called a neighborhood. Okay, so whatever we have learned in our real analysis, so they are just open neighborhood. An open neighborhood is just a neighborhood which is an open set also. But in general, a neighborhood is a neighborhood. It's not necessarily an open one. Okay, all it needs to have an open set in between the point and the set itself. And we make habit of assuming open sets, neighborhoods to be open neighborhoods if nothing is stated. Okay, in the complex analysis, if nothing is mentioned and if it is shared that it's an open neighborhood of a point, it's a neighborhood of a point, then you just assume without loss of generality that it's an open neighborhood. Okay, it's not any neighborhood. So if nothing is mentioned, a neighborhood means an open neighborhood. Now let us come to define the metric space. Perhaps most of you have seen this in course of your career, but I'm just kind of recollecting all of them. So if you have a non-empty set and if you have a distance function, so D is a function from x cross x, the Cartesian product of x and x to the real line R, that satisfies these three axioms, that it's a non-negative function, D of xy is greater than or equal to 0 for all xy, and it is 0 if and only if x is equal to y, meaning D of x comma x is 0, and that is the only possibility when it is 0. And D of xy is equal to D of yx. This is what is called the symmetry. And the third point is called the triangle inequality, that D of xy is less than or equal to dxz plus dzy or any xyz. Then D is called a metric on x. If a function D satisfies these three axioms, then D is called a metric on x, and this pair x comma D is called a metric space. Okay, so as soon as we have such a distance function on a set, we get a lot of things. Number one, if you just look at this BXR, so this is the standard notation that we use to denote an open ball with center at x and radius r. So this means it collects all such points y from x whose distance is less than r from x. Okay, so you can have a pictorial view of this. It's just an open ball with radius r and center at x. Similarly, you have closed ball. The same thing, you are collecting all such points y from x such that this d of xy is less than or equal to r here. So this is what is called a closed ball. Okay. Now, if you collect all such open balls, the script B is a collection of all such open balls that lie within X. Okay. Choose all possible points from X to be its center and choose R in such a way so that this BXR lies within X. It does not go beyond X. Okay. If you collect all such balls in this way, then this collection, it generates a topology on XT. Nevertheless, if you take any collection of subsets of X, it generates a topology because you just declare this collection to be a base for the topology. And we know if a base is given for a topology, how to get back the topology? How do you get back the topology? You take all possible unions, okay, from the members of this collection. So this is how we generate a topology, right? For which the given collection is a base. So if you declare this collection to be base for something, base for a topology, definitely you will get a topology on XD, and this is what is called the metric topology on X induced by the metric D. Okay. So if you have a metric defined on a set, this was just a set, this X was just a non-empty set, and you have defined a metric on it, then it induces a topology. Okay, so every metric space is a topological space whose topology is induced by the metric. So for example, if you just look at the Euclidean space R, real line, then our usual modulus, it gives a metric. You just define d of xy is equal to modulus of x minus y. Then you can easily verify that this d is a metric on R. And this is the Euclidean metric indeed. The topology that this metric induces is what is called the Euclidean topology on R. And we are habituated with this topology on real line. We work with it day in and day out. So similarly, if you move from one to several variable, for example, if you choose two different points, any two different points, x and y, each is an n-tuple from Rn. Since we have discussed about R, so let us choose Rn with n greater than or equal to 2. And if we define, this is what is called the 2 norm, norm x minus y2. This is the way the metric is defined here. D of x comma y is equal to this, where we know what is the Euclidean norm on Rn. So this is precisely given this way. Okay, x1 minus y1 square plus dot 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 plus xn minus yn square and square root of that. This is what is called the Euclidean metric on Rn. And the topology on Rn, whatever we are habituated with, we have seen so many times in our several variable calculus, is precisely the metric topology induced by this metric. This metric is called the Euclidean metric on Rn. And in particular, if you choose the complex plane, we know what is meant by modulus of a complex number. If you have a complex number x plus iy, then the modulus is this quantity. This is a non-negative quantity. We all know about it, right? This is nothing but the distance of this complex number from the origin. So its modulus, it induces its Euclidean topology. And how is that defined? We all know. Okay, if you have two complex numbers, alpha and beta, with alpha being alpha 1 plus I alpha 2 and beta being beta 1 plus I beta 2, then modulus of alpha minus beta is precisely this quantity. Okay, you all know about it. And the topology on the complex plane, what we are habituated with, is given by this metric indeed, and it is the Euclidean topology of C, which is equivalent to the Euclidean topology of R2. As we have seen that R2 and C, they are homeomorphic with each other. Okay, so whenever someone says R2 and C, they are homeomorphic, that means the underlying topology is the Euclidean topology on each of them. So if you have a non-empty set X, and if you define a metric D, I should not say, I should not call it a metric, just call it a function. If you define D from X cross X to R, and it is defined this way. It is 0 if x equal to y, and it is 1 if x not equal to y. Then one can verify. I request you guys to verify that this is a metric. It satisfies all three axioms which are described above. And this metric is called the discrete metric on the set X. And as you know, if you have a metric, you have a topology. We have seen that already. And the topology that it induces, this metric induces, is the discrete topology. We have discussed about discrete topology yesterday. Okay, it's a topology where every subset of X is an open set. And if all one-point sets, they constitute a base for this topology. So you just look at the values of this metric. They are discrete. At one, at one end it has value 0, and at the other end it has value 1. So it chooses two discrete values. So this is perhaps the reason it is called a discrete metric. Yesterday someone asked me this question: why is it called a discrete topology? This is because the behavior of this metric, it is called the discrete metric, and the corresponding topology is the discrete topology. You can verify this easily. Okay. So as I have said, if nothing is mentioned, we always consider Euclidean topology and C. And now I have a question here. So if you define the map F on the set of complex numbers, that Z goes to Z bar. We know this Z bar. Z bar is the conjugate of Z, right? That is, if if Z is X plus IY, we all know that Z bar is its conjugate X minus IY. Now the question is this a homeomorphism? Definitely it's a 1-1 map, right? There is no doubt about this. And it is also onto. So it's a bijective function. Now the question is whether this is continuous and its inverse image is continuous. Please verify this. Do you guys know whether this is a homeomorphism or not? What should be your answer? What do you think? Is this a homeomorphism?
Yes. Yes.
Is it continuous, you think?
Yes, continuous.
Yes. Yes, it is continuous.
Continuous.
And what is the inverse image of it? How do you define the inverse? In a similar fashion, right? Again, the inverse will be defined at Z goes to Z bar, right?
Yes. Yes.
Yes. Yes. This is a peculiar function. Anyway,
Yeah.
you just study this. It's very easy. Nothing to share. Yeah. And we use this spatial domains. For example, the spatial sets, the spatial open sets in the complex plane. For example, the unit disk. This is what is called the unit disk, and we use this notation, this bold D. This is the standard notation for the open unit disk. What does it mean? It consists of all such complex numbers whose modulus is less than 1, and similarly the closed disk. It consists of all such Z whose modulus is less than or equal to 1, and one can verify that this is actually the closure of the previous set. And this bold H is called the open upper half plane. That means for all such complex numbers for which the real part is strictly positive. So this is precisely all complex numbers that lie above the x-axis. Okay. So these are the standard notations and the standard sets. So these are the basic neighborhoods of any metric space. Indeed, here in case of the complex plane, they are the basic open sets. So we use this notation: disk of radius r and center z0, this way. Sometimes we denote it by dz naught r, sometimes bz naught r, but nevertheless they represent the same set. Okay, and it's closer this way. And the unit circle, like we have defined the unit disk and the closed unit disk. The unit circle, it has several notations like this.
So can you
It means,
explain one more time real part of z greater than 0 is the upper half line?
Yes, sir. Real z greater than 0
Real part
actually
of z
right
greater
half
than 0
plane.
is the right half line.
Right half
Long
plane.
exponent.
oh, I'm sorry,
Yes, yes,
I
yes.
think
Right after.
this will be imaginary jet.
Yes, imagine.
Yes. I'm sorry. Thank you very much. This is once again it needs correction. It's not working. Just a minute. Somehow it's not working.
So, Sourav, what you can do, if you have the mouse, you can scroll it, it will come.
Yeah, I am scrolling it down, yet somehow it's,
Yeah.
I
Happens.
think it will work now. No, it's not. Somehow it's, this is right up plane. Yes, I wanted to mean imaginary part of Z is positive. I think now it will work. Yes, thank you. Yes, thank you very much. So similarly, we have the unit circle and this notation for the unit circle. Okay, and the boundary of an arbitrary disk with center at z0 and radius r. This is also a circle whose center is z0 and radius is r. And we have annulus of this type. This is what is called an annulus. You have an open disk, you remove another closed disk from it. So this is what is called an annulus. Okay. So you just look at this picture. You are removing the closed disk that lies inside, not the open one, the closed one. Okay, with the boundary. Then what you get is an annulus, and you can do it for any two open disks. Okay, not just the unit one. Here, I have chosen the unit one, the unit disk to be the bigger disk, but you can do the same with any two disks with same center, nevertheless. So, we follow this convention in complex analysis. As I said, if you just look above, the way we have defined the open ball or open disk of radius r and center at z0. So this is sometimes, we use just this notation, z minus z0, its modulus is less than r, to denote this open disk. And similarly, this notation for the closed disk and this notation for the circle. We use this. So if you see this in the later half of this course, so don't get confused. Now, I briefly describe what is a product topology. So this is something that you will perhaps need in this course. So what is a product topology? It's I guess we have done a master's in mathematics knows it. So you have a family of topological spaces, okay, that runs over an index set J. You have this family X alpha tau alpha. And the Cartesian product of these sets, we know what is meant by Cartesian product of an arbitrary family. This is nothing but all possible functions from the index set to the union of all X alpha, such that this x of alpha, meaning the alpha component of this function, will belong to the topological space x alpha, and it holds for all alpha. So this is what is called the Cartesian product as a set. I am not talking about any kind of topology now. This is just a Cartesian product of sets. And how does an element look like? It's just a tuple. It's just a tuple where the alpha component is x alpha. Okay. In case when this index set is the set of natural numbers, we call it a sequence. Okay. So now the question is, if x alpha, tau alpha, they are topological spaces, then how to define a topology on this product? So let x be this x be the Cartesian product of these sets, and you consider this collection script B. It's a product of u alpha. Definitely alpha runs over this index set, and we know what is meant by this set. We have defined what is meant by this Cartesian product, so it is known. But this u alpha is an open set. It belongs to tau alpha. It's an open set in capital X alpha. And not only that, all what finitely many u alphas are actually equal to X alpha. So here we are considering Cartesian product of open sets of this type u alpha, where the alpha component of the Cartesian product will come from tau alpha. Okay. Nevertheless, but you see, u alpha equal to X alpha for almost all alpha. There are only a finite number of alphas. It could be where this u alpha is not equal to X alpha. So now, if we declare this collection to be a base for a topology, okay, that means the topology that this collection generates is called a product topology on X. So this is the product topology on X. So if we just look at Rn with the Euclidean topology, our Rn with Euclidean topology, this is nothing but the product topology of n number of Euclidean spaces, R modulus. This modulus is the metric here in case of one variable, and we have the two norm. This is the metric for the n variable, so one can verify this. Now, I'd like to define compactness for arbitrary topological spaces, but it's going to be too much. So I have just defined it for Euclidean spaces. So a subset of Rn, whenever I said Rn or C, and nothing is mentioned about the topology, you assume without loss of generality, it's just the Euclidean topology. This is called compact. If it is closed and bounded, in particular, if E is a subset of C, then it is compact if it is closed and bounded. So if you just look at a closed rectangle in the complex plane or a closed disk, they are compact sets. And all finite sets are also compact sets. So we have this this theorem, we all know about it, that the continuous image of a compact set is compact. We are talking about C and Rn only. We are in this zone. Now, what is connectedness? So this is defined in just hold for a second. So yeah. So what is connectedness? A topological space X. This is in the general setting. This is not the Euclidean setting only. It holds for all topological spaces. A topological space is called disconnected if it can be expressed as a disjoint union of two of its open sets. Okay, such that this G1 and G2, they both are non-empty proper open sets. This is transparent from this condition that they are disjoint. Okay, if one of them is phi, then this is also phi. So if there are, better to write non-empty open sets. So I'd like to write here again. This is not working somehow. So yeah, I just want to mention there are non-empty open subsets G1 and G2 such that this thing happens. Okay, non-empty proper. You just make all confusions out. Anyway, so a space is said to be connected if it is not disconnected, if you cannot find out such disconnection. Okay, so a subset of a topological space is called connected if it is connected with respect to its subspace topology. Every subset itself is a topological space with respect to its subspace topology that it obtains from the original space X. So now just look at some examples. So what are the connected subsets of the real line with Euclidean topology? They are intervals. I request you guys to verify this. So this is a part of the real analysis course. I think you all have seen this as a theorem in real analysis, but just recall the proof. I request you guys. And what are the intervals? The intervals of real line are of this type, either open or half open, or closed, or an open ray, or a closed ray, half closed ray. It's somewhat like this. And if we move from real to complex, an open or closed disk is a connected set, right, in C. So another question is, if I talk about a circle in the complex plane, is it connected, you think? You just look at the definition. A subset is connected if it is connected with respect to its subspace topology. Now, if I talk about a circle in the complex plane, C, okay, it has its Euclidean subspace topology. Now, with respect to that subspace topology, is it connected? I have talked about the open and closed disk. Now, what about the boundary? Is it connected? What do you guys think?
Yes, connected.
Yes, indeed, it is connected. You cannot find out a disconnection here. So the answer is yes here. Nevertheless, now if you take union of disjoint balls in C, then this is definitely disconnected. So we remember this theorem. The continuous image of a connected space is connected. Okay, and if you have a connected set E in a space X tau, then any set that lies in between E and E closure is also connected. And the other theorem that the product of connected spaces is connected, okay, in the product topology. Whenever we talk about product, definitely we are taking the product topology. Now, what is a path? A path in a topological space is nothing but a continuous function from a closed interval to this space. It's just any continuous function defined on any closed intervals, where the right-hand side is the given topological space X. So if you have a path f from defined on this closed interval to X, then this fa, the left end point, the image of the left end point is called the initial point, and the image of the right end point fb is called the final point, or the final point of this path. So a space is called path connected if for any 2 points in that space there is a path joining these 2 points. This is what is called a space being path connected. Any 2 points in the space can be joined by a path, okay, and the path lies within the space X. So this is a famous theorem that we have learned in topology. I just mentioned this: a path connected space is always connected, but the converse does not hold. It's not easy to construct an example that the converse does not hold, meaning a connected space that is not path connected. It's difficult, it's not easy, but there exists such example. So always remember this. Path connected space is connected, but the converse does not hold. One can find out examples in any standard topology book. So they are all path connected. This set, the open disk, the closed disk, and the annulus of this type. This is an annulus with center A, and it's determined by these two radii, R1 and R2. Okay, just look at this image. So they are all path connected, meaning given any 2 points in these sets, you can join them by a path. You can join these 2 points by a path, and that path will totally lie within the set. Now we come to our machinery. An open connected subset of the complex plane is called a domain or a region. So this is a terminology that is used in complex analysis. So what is a domain in C or region in C? It's an open connected subset. So later on, you will see that an open and connected subset of C is path connected. So it is there in the tutorial sheet. So nevertheless, so this was a brief introduction of the topological things, whatever I record for this course. Now I move to the basic complex numbers. Okay. So I begin with the exponential function. So this is what I am going to start. The exponential function.
Sir, I have a question, sir.
Yeah, please.
Sir, you have just mentioned that region and domain are same, both are same. But
Yeah,
in the
that is
complex
what.
book, I have seen the different definition.
What is that?
This says that a region is a domain having may have its boundary or doesn't contain, may not contain its boundary. The definition is like that.
No, I did not say that once again, please.
The definition is like that a region is a domain which may contain, may not contain its boundary. Like that, the definition is.
Well, the region is, if we talk about open sets, then certainly it does not contain its boundary, right?
Yes.
So this is a standard thing. So, we call something to be a domain or region. That means it is open and connected. That's what is standard. Okay. So
Yes,
that's
sir,
what
for
we will follow.
Yes, sir, for domain I have no problem. But yeah, for
Yeah.
region,
So
I have
that is
studied
what
differently.
we follow anyway.
Okay, sir.
So the exponential map. The exponential function. So you know how to define exponential function on real line. I am not going to discuss about this. I am going to discuss about how we can define exponential function on the complex plane. So this function, first of all, it has got this notation. We use this notation exp, or better I write exponential of z or e to the z. So this is a function from C to C. So this is defined by, if z equal to x plus iy, then you define e to the z or exponential of z to be e to the x times cos x plus I sin x. Now the question is that if you just look at the definition, This e to the x is known.
Cos y plus I
cos
sin
y
y.
plus iota sin y.
Sorry.
Cos y
Oh,
plus
oh,
I sin.
oh.
Yeah, it will be one. Yeah.
Again, I have written, I'm sorry. So this is happening too frequently. I am thinking something and I am writing something else. Thank you very much. So if you just
So
look at
sorry,
e to the x,
sir. Sorry to interrupt you. There's very low voice coming, sir.
who is that?
Sir, voice is not coming properly, sir. Very low voice is coming.
Just a second.
No,
My
no, voice is
audio,
clear. It's audible.
full somehow. So is it coming?
Yes,
Right.
yes.
Okay.
We are getting the full voice. Are you using headphones?
No, I am not using
For us?
headphones. If I
No,
use
sir, no, sir.
headphones, then the
No,
level
sir, I
will
am
go
not.
down.
I'm not
Yeah,
using.
yeah. I'm asking to Faroz Ahmad, but
No,
are
sir, I
you
am not.
using it? So
No, I am not. I am not
if
using.
you, yeah, speaker
using it.
need not use the headphones. If others use the headphones, they're getting the good sound.
Okay. So yeah. So can everybody hear me now clearly?
Yes, sir.
Yes, sir.
Yeah. Thank you.
Yes, sir. Continue.
Thank you. So if you just look at this quantity, this e to the x, so this is something that we know from the real numbers, right? Exponential of a real number is well defined. So this part is well defined. This part is well defined. And if you just look at cos y and sin y, they are also well defined. We know what is meant by cos y if y is a real number, and we know what is meant by sin y if y is a real number. So we know all three things together. Okay, all three things are well defined. So this quantity is well defined. So this function, this exponential function, it is defined this way, is well defined. So this is the first thing that we notice. So yeah. Now, if y is 0, then this z is real. Okay, then we have the real exponential, right? If y is 0, then we have the real exponential. Okay, and we have e to the z to be equal to e to the x then. Okay. Now the question is, yeah. Now the point is that if you just look at two points, say z1 equal to x1 plus iy1 and z2 equal to x2 plus iy2, given two distinct, distinct or same whatever, two complex numbers, then what is e to the z1 plus z2? So I am just directly writing it here. I'm just directly writing it here. E to the z1 plus z2. This is, if you just look at, this will be to the x1 plus x2 plus I times y1 plus y2, which is precisely e to the x1 plus x2 times cos y1 plus y2 plus I sin y1 plus y2. Okay, and if you evaluate these two, if you evaluate e to the z1, which is e to the x1 cos y1 plus I sin y1, and e to the z2 accordingly, then it's just a few steps of calculation. It will give you that these two quantities are equal. E to the z1 plus z2 is equal to e to the z1 times e to the z2. You can easily verify this. It just takes three or four steps of calculations, nothing else. You just evaluate this. We know how to evaluate cos y1 plus y2. Okay, how to write it explicitly. We know the formula. So you just verify this. I'm not writing all those steps here. Once again, the pen is not working. Just a second. Yeah, you just verify this. It holds for any two complex numbers z1 and z2. So we have this. Okay. So this is the first property that we have about the exponential. Now, the second thing that you notice is that what is the range of this function exponential? Okay. The range of exponential, does it contain the origin 0? That is a question. The answer is no. So e to the z is non-zero for any z in the complex plane. Why? How do we prove that? How do we prove that? Because
real part should be equal to 0, sir.
hmm?
Then the real part should be equal to 0. That is, the exponential of x should be equal to 0, which is not possible.
No, that is possible if y exponential of x is 0, then it's a product of 2, right? E to the z is e to the x cos y plus I sin y, right?
Because cos and sine cannot be simultaneously 0.
Yeah, that is the point. So it has to be 0. The thing is that if you just look at e to the z times, yeah, you guys are correct, e to the minus z. And what is that? What does it give you? That gives you e to the z minus z, right? So this is what we have seen. E to the z1 plus z2 is e to the z1 times e to the z2. So this is precisely e to the 0. And our real function knowledge, okay, we know about e to the x when x is real. So e to the 0 is 1. That is already known. Okay. So this e to the z, it cannot be 0 then. Okay. So therefore, e to the z cannot be 0. Because if it is 0, then the right hand side cannot be 1. Am I correct? Yeah, you guys are correct. So this cannot be 0. And so this e to the x has to be 0, which is not possible. So, and the next thing is so these are the properties of the exponential function. And the next thing we would like to state is that if x is real, then what is e to the ix? E to the ix, its modulus is equal to 1, meaning it lies on the unit circle. How do you prove that? Because e to the ix squared, what is that?
Sin
What is the
square x
definition?
plus, yeah, sin square x plus cos square x, and that
Yes. What is the definition of e to the ix? If you just look at this definition, e to the z is e to the x times cos y plus I sin y. So e to the x, e to the ix will be precisely why it is cos square x plus sin square x. Can you tell me?
So we can write e to the power iota x as e to the power 0 plus iota x. This means imaginary part is x and real part is 0. So imaginary part
Yes.
can be written as
So
cos.
it's simply, yes, you are correct. Yeah. So this is simply cos x plus I sin y. Sorry, cos y. Yeah, x. Here we are dealing with x, and x is real, and we know the modulus of this complex number is 1. Okay. So this is precisely cos squared plus sine squared, as he said. Yes, correct. And now we are in the real variable arena, so it's fine. Everything is fine. So this means that this is always 1. So this is one thing that we are learning, that if we choose any purely imaginary number and put this on the top of exponential, its modulus is 1. And the next thing is e to the z e is equal to 1 if and only if z equal to 2n pi I, where this n runs over the set of integers. How do you prove that? So it requires proof. Can anybody suggest me a proof of this? Well, if z is of this type, if z is 2n pi I, then it's easy to see, right? Then e to the z e is equal to cos 2n pi plus I sine 2n pi, and we know that this is always equal to 1 from our knowledge of real analysis, that this part is 0 and this part is 1 nevertheless. So now what about the converse? If you assume that e to the z equal to 1, okay, so let e to the z is equal to so this is equal to 1. Then what do you have? You have e to the x cos y to be equal to 1, and this portion is 0, right? Comparing the real and imaginary part. That is what we do. So that means sine y is 0, right? Because e to the x cannot be 0. So if sine y is 0, then you know how does y look like. So therefore, from this part, we have y is of this form in pi, right? Where this in runs over complex numbers, sorry, all integers. And can you finish the rest of the proof? So from this equation we have this, and from this equation what we have? What is cos n pi? Cos n pi is minus 1 to the n, right? Right? Therefore, from e to the x cos y is equal to 1, what do we have? What do we have? On the left hand side, we have e to the x times minus 1 to the n is equal to 1. Okay. And what does it imply? What does it imply? So this means, oh, it's not working again. Just a second. Yeah. So it implies that e to the x is minus 1 to the n. right? Now we know that to the x is
Manushi Gupta, could you please mute your mic?
positive. Since this is positive, therefore this n is even. Okay, it follows from this equation. You just look at this e to the x. It is always positive, so the right hand side is positive. So this n has to be even. Okay, so therefore n equal to 2k. Okay, where k runs over the integers. Therefore, z is equal to 0 plus, and x is 0, right? So e to the x equal to 1. Just a second. Then x is 0. So e to the x is 1. That is what we obtain. So this means x is 0. Okay. Now we are in real analysis. E to the x is equal to 1 means x is 0. And we have n equal to 2k. So, and y is n pi. That's what we obtained earlier. So this is 2k pi, where k belongs to z. Therefore, z is equal to 0 plus 2k pi I. Okay, so we are done. So whenever we find that e to the z is equal to 1, whenever we find e to the z is equal to 1, that means that z is of this form, 2 pi 2n pi I, where n runs over the integers. Okay, we always remember this because this is something that is used rapidly in complex analysis. We just try to remember this. Nevertheless, so these are the properties. So it follows immediately from the previous property that if you have e to the z1 is equal to e to the z2, okay, if you have this, then this z1 minus z2, it has to be of this form, 2n pi I, okay, and the converse also holds. Where this n belongs to the set of integers. Okay, so this follows immediately from the previous result. So if you find e to the z1 is equal to e to the z2, that means z1 is always z2 plus 2n pi I, where this n runs over the integers. So this is the entire set for which this thing happens. Nevertheless, so these are all about the basic properties of the exponential function. Now we can talk about argument of a complex number.
Sir,
Yes, please.
is e to the power z is 1 1.
Say that once again.
Is the exponential function 1 1 function 1 to 1?
That is what is seen here. Is it 1 1?
No, then under what condition it become 1 1? Okay, it's not 1 1 in generally, but under what condition it become 1 1?
It is defined on the whole complex. It is defined on is whenever I have defined exponential, it is defined on the whole complex plane. So on the whole complex plane, it is definitely not 1 1. That we can see easily, right? We have seen that, if e to the
over a
if
strip
e to
of
the
length
z,
2 pi.
Yes, yes.
yes, if you restrict it over a strip of length 2 pi, then it is definitely 1 1. But
Yes,
here it is defined for it is defined for all complex numbers. Definitely it is not 1 1. And it is not onto also, because 0 is not there. But other than 0, everything is there. You will see it. Nevertheless, so argument of a complex number. So what is a complex number? Until now, we all know about the geometry, right? So if you have the x-axis and the y-axis, and if you have a point somewhere here, say, if you have a point, say z is equal to x plus iy, okay, then you just, this is not properly done, you just join this with the origin. So this should be a straight line. I could not draw it properly. Anyway, so you just notice two things. We all know that the length of this line segment, so this is the origin, the length of this line segment is precisely mod z, which is x squared plus y squared square root. And the angle that it makes with the real axis, it makes an angle with the positive direction of x-axis. So this is, if we call this theta, then this theta is called the argument of this complex number. Now, you just notice one thing. So if we measure angle in this anti-clockwise direction, we call it the positive direction. If the angle is measured in the clockwise direction, this direction, okay, in this direction also the angle can be measured, right? So this is what is called the negative direction. Okay, so this is the positive direction, and this is negative direction. Okay, so again, the measurement should start from the real axis. Okay, it starts from here and it goes either this way or this way. If it goes in the anti-clockwise direction, we call theta is positive, otherwise theta is negative. We will see how it goes. Nevertheless, if you call this angle to be theta, as I have written over here, if you call this theta, then you just notice you can make one round. You start from here and you make a full round and come back to this point. If you start from here, okay, and make a whole round in the positive direction, okay, and again come back to this point. So you are moving in the positive direction always, okay, in the positive direction, and you are coming back to this point. So how much you have traveled? According to angle, you have traveled 2 pi, right? So if you just look at this angle theta, this angle, this can be described as 2 pi plus this angle also, isn't it? If this is theta, then this can be represented by 2 pi plus theta also. They represent the same angle geometrically. I am talking geometrically. Okay. So this is the reason. This angle, whatever we say, pictorially, whatever we are just witnessing. So this is not unique. This is not unique. So this angle is called the argument. Indeed. So the argument is not unique. Okay. So this theta is called the argument of the complex number Z. Okay, so did you all understand that why it is not unique? So if I start from here and move this direction and end here, this angle is theta. And if we have start from here and move this direction and complete this circle and come back here to the same point where we started from and again move until this. So this angle is 2 pi plus theta, right? So geometrically they represent the same angle. Geometrically they represent the same thing. So this is the reason if we say theta is the argument of Z, so this is not a well-defined thing. And the argument of a complex number is not well-defined. This is the reason. So here we choose, polar coordinates. How is that? We have chosen Z to be x plus iy. So this can be recovered if we choose x to be r cos theta and y to be r sin theta, where precisely this r is modulus of Z, where this r is modulus of Z, which is root over x squared plus y squared, and theta is the angle that this point makes with the real axis. Okay? And theta is the angle, and theta is the argument. With x-axis, okay. Of course, the positive direction of x-axis. Nevertheless, as I said, this theta is not unique. So if theta is not unique, then whatever we call the argument is not unique, and thus this argument is defined to be a multi-valued function. Okay, so we write theta is argument of Z, and this argument, okay, I forgot to mention one thing, we should, whenever we talk about argument, we choose non-zero complex numbers, okay? So let Z belongs to C and Z non-zero, okay? So this argument is a multi-valued function. And this is defined for Z not equal to 0. Now, if it is not well defined, if it is multi-valued, then what we work with? Which theta we choose? As we have seen, if this angle, whatever we have seen above, for example, if this angle is theta, then theta plus 2 pi or theta plus, again, the pencil is not working. Just a second. As we have seen, if theta is this angle, running from here to this point, then theta plus 2n pi also represent the same angle. So for this reason, let us fix something that we work with. Meaning, let us fix something that makes this function a single valued function, a well-defined function. So this is the reason we call this, this is something that we will work with. We call it the principal argument. The principal value of this arc z, which is denoted by, we shall denote it by arc with a capital R, capital A. To be the value of theta that satisfies okay. So this is what is called, when the value of the argument lies in between minus pi and pi, with one being included and the other being excluded. I am telling you why. So if you just look at the picture above, so if theta is this angle, then 2 pi plus theta is again representing the same angle. And once again, 4 pi plus the same angle theta represents the same angle. Meaning, it's a 2 pi periodic function. Right, it's a 2 pi periodic function. So we have to choose an interval of length 2 pi. Here, we are choosing this interval, minus pi and pi. Okay, but what happens if we include minus pi and pi both? So then it will be a mess. For example, if you just look at a point here, so if I say minus pi, then it is defined, it is measured this way, in this direction. Okay, so let us draw this once again. If you have a point here, say Z, okay, and we are choosing minus pi and pi. You see, any point lying in this complex plane can be represented by this interval. Okay, so wherever Z lies, here or in this quadrant or somewhere here or somewhere here, if it lies in these two quadrants, then we measure the angle in the negative direction. If it is here, then we measure the angle in this direction so that it becomes minus something. Okay, so if you take a point here, then this angle is minus pi at most. So it cannot go beyond minus pi. And if you have something, so that means, how do you measure this? This is also, you measure in the negative direction. So it lies between 0, minus pi and 0 here. And if you have any points on this quadrant, then you, for example, this point or this point, then you start measuring angle in this positive direction. Okay, so that it does not go beyond pi. because from here to here, if you move, if you complete until here, then you have pi here. So it should not go beyond plus pi and it should not go beyond minus pi. Now, if you look at this line, the negative x-axis, and if you choose a point from here, you can say that it makes an angle minus pi, and you can say it makes an angle plus pi also in a similar fashion. It cannot be both, so we have excluded one. So this is the reason we have excluded minus pi here and included plus pi. You can include minus pi and exclude plus pi. Nevertheless, so this is an interval in the real line of length 2 pi. You see, this theta is real. This theta is real, first of all. And theta belongs to this half open interval. Okay? So the thing is that you can choose any interval in the real line with length 2 pi. For example, you choose say 0 to 2 pi, one included and other excluded. Okay, so 2 pi is included and 0 is excluded. Then how do you measure the angle? So you see here your angle lies in between 0 and 2 pi. So given any point anywhere here, okay, so you will move in the positive direction always. You just look at here, everything is positive here, there is no minus thing. So if the point is here, we measure the angle, we always measure the angle in this direction. So if the point is here, then we consider this angle itself. Okay, this is the angle. We are not measuring in the negative direction. So the argument will lie in between the 0 and 2 pi. So indeed, if you have any interval of length 2 pi, meaning if you have, say, point, say, alpha and alpha plus 2 pi, one included and another excluded. Okay, you can make this thing, we are following the same convention. So let us exclude this left hand and include the right hand. Then it all depends upon whether this alpha is negative or positive. Okay, if this alpha is non-negative, then you are measuring the angle always in the positive direction. But if alpha is negative, say if alpha is, say, minus pi by 4, then what will be your right hand point? The right hand point will be how much? What is the interval then? Are you guys there? So the right hand point will be alpha plus 2 pi, right? So which is
7 pi by 4.
maybe 7 pi by 4, as you were saying. So then, from which line you will start measuring the angle from? If you have this interval, okay, then how would you start measuring the angle? If you want your argument to lie within this interval, okay, then it's minus pi by 4. 0 is somewhere, and on the right hand side you have something positive. So if this angle is minus pi by 4, okay, then you are considering this much negative and the other parts are positive. Okay, so this is how it is measured. If you choose a point here or here or here or here until here, okay, so this is excluded. So until here you are measuring in the positive direction. Did you get me?
Kuladev, please mute your mic. Please, Kuladev, please mute your mic. I'm sorry, Sourav.
Yeah, it's fine. So do you guys understanding? If we look at this interval and if we say, let us have our argument in this interval, the argument will lie within an interval of length 2 pi, a half open interval of length 2 pi. That we have seen and we have made it clear. Okay. Now the question is, as I said, you can choose any half open interval of length 2 pi. Okay. Now, if you choose this interval in particular, minus pi by 4 and 7 pi by 4, for example, this is closed. So how do you measure the angle? How do you express your argument then? For a complex number that lies here, it will be positive. The angle will be measured right from here in the positive direction. If a point lies here, then also the angle is measured in the positive direction. If a point is here in the third quadrant, then also you are measuring the angle in the positive direction until this line, until this point. So this is the point where you stop measuring from the positive direction. Okay, and it is minus pi by 4. So this is from here to here. So this angle is minus pi by 4 actually. So if a complex number lies here somewhere, if z equal to x plus iy, that lies here, then what is the argument of this complex number? You join this and you measure the angle in this direction. Okay, so that it belongs in this interval. So is the idea clear to all of you? So this is the idea of argument. It is a multi-valued function, number one. And if you want to make it single valued, you choose a half open interval in the real line, okay, of length 2 pi. You can choose any half open interval on the real line with length 2 pi. You can choose left half open closed, right closed, or left closed and right open. That is also possible. So that is what is argument, and that is what is the principal argument. So we deal with, in complex analysis, or our standard convention is to follow the principal argument. The principal argument is something where theta lies between minus pi and pi. Okay, so half of the thing we are measuring from the negative side here, and half of the thing we are measuring from the positive side. I am saying half and half because half of the quantity is negative here and half is positive here, with the fact that one of the endpoints is included. Okay, so this is what is argument. So you can verify that. If you choose argument to be your argument of z, okay, this is precisely this set. As I said, it is a multi-valued function. So this is the principal argument plus 2n pi, as I said, where this n is any integer. Okay. Now, what do you guys say about I shall define continuity and limit? We shall see that this function is not a continuous function. Nevertheless, we will see that maybe in the next class. So there are some properties of argument. So they're very easy to determine. So have you guys understood what is argument of a complex number? It's geometrically the angle that it makes with the real axis. And once again, the angle can be measured in the positive direction or in the negative direction. It's entirely up to you. It depends upon what interval you will choose. It is a multi-valued function and it is a 2 pi periodic function. So any half interval of length 2 pi will work. We can choose it to be its range, and we deal with day in and day out with the principal argument. And the principal argument is something where we choose the interval of 2 pi, length 2 pi, to be this interval, minus pi, pi. One side is open, another side is closed. Okay. So if you have any question, please ask me freely. I'm not going to say anything more today. I want to stop here. So if you have any question, please tell me.
Sir, I have a question. Sir, I have a question.
Yeah, please.
We have told that the principal value, in case of principal value, the keep the range between minus pi to pi. But you also told that we can take any half open interval of length to pi, as for example, minus pi by 4 to 7 pi by 4.
Yes.
Then if we take the principal value of argument equal to 3 pi by 2, then is it true?
No, the principal value is something that is defined this way. Okay, principal value, we call, when theta belongs to this interval, we call this principal argument. But argument is, argument is not a single valued function. It is a multi-valued function. So when is it single valued? If you choose to restrict your right hand side to be a half open interval of length 2 pi, and that is your choice. And when the choice is minus pi pi, this interval in particular, this half open interval, we call it is this argument to be the principal argument. This is just a name.
Okay.
When we choose this interval, we call it capital ARG. This is argument. Nevertheless, you can choose any interval. That will also be one part of the argument. So when it is single valued, it is called a branch of the argument. We use this term, branch of the argument. When it is single valued, if you want to make it single valued, you have to choose something that has length 2 pi, an interval of length 2 pi. And every, whenever argument is single valued, we call it a branch of argument. Okay.
Okay.
So this is one branch. This is one of the branches. And we call this branch to be capital ARG. That is the principal branch or the principal value. So this is just a name. You can choose any other, any other interval of length 2 pi. As I said, you just look down. As I said, you can choose alpha and alpha plus 2 pi. You can choose any alpha. You can choose this alpha to be, 1.001. Doesn't matter. You can choose this alpha to be anything. Yes. You can choose this alpha to be, say, 2.0001. Who cares? Okay. And have alpha and alpha plus 2 pi, or alpha plus 2 pi. The right hand side is open. Our business is to measure the angle. This is just, business of measuring angle. Given a point in the complex plane, how can we measure the angle from x-axis? This direction or this direction? Now, every branch of argument, what does it give you? It gives you a tool. How do you measure the angle? If you say, I will measure the points that lie in between, this zone in the negative direction and the others in the positive direction, then the interval will be accordingly, as I said, minus pi by 4 and 7 pi by 4. You are measuring 0 to minus pi by 4, this zone. All points lie within this zone. The angles are measured in this way, in the negative direction. All other points, the angle will be measured in the positive direction. Okay? So it's entirely up to you. It's entirely up to you. So you have to fix a line. Okay? You can fix this line also, for example, that you will measure all angles until here in the negative direction. All points lie within in the negative direction. And the rest of the points you will measure from the positive direction. Then it will be accordingly. Then if this is, say, pi by 2 plus 3 pi by 2 or something, this angle 3 pi by 2 or something, then it will be minus 3 pi by 2 comma, minus 3 pi by 2 plus 2 pi, this angle. So it's entirely up to you. How do you measure? But the standard convention is you measure half of the points in the negative direction and half of the points in the positive direction, so that it becomes minus pi and pi. And this is what we are used to. Okay, half of the points. Minus pi means from here until this point, and plus pi means from here until this point. So this is how we measure. This is the standard practice, and it is called the principal value of the argument. It is called the principal branch of the argument. Okay. Any other question, please? So
Yes,
this
sir.
is simple geometry. There is nothing, it's very transparent. And how do you measure the angle? As simple as that. If you have any more question, please.
Yes, sir. Sir, we actually use this principal argument to find the exact location of complex number on the complex plane. But when actually we try to calculate the principal argument of some complex number, sir, that time we first go to the complex plane and find the location of the complex number. Basically, if we usually use the polar coordinate system. Suppose we have some a plus ib as a complex number, we just write a equal to r cos theta, b equal to r sin theta, calculate the modulus r, and then by dividing we calculate theta. But after the calculation, that gives the wrong information. For instance, if I choose suppose minus 1 minus I as a complex number, this being in the third quadrant, but when we use this type of technique, we fall in, I mean the complex number fall in the first quadrant, so we get a problem in the calculation. So does this mean to get the principal argument we first have to go in the organ plane? I mean this we need to find first of all the location, then go to the principal argument, or we
No,
can
this is
first
what I am. Yeah, what I am showing here is how geometrically, what it is exactly, what is happening here. That's what I am just trying to show. What exactly is happening here? This is exactly is happening here. But if you talk about the principal argument, as I said, we choose this interval. We choose this interval. The point is that given any complex number, you find out theta, as you said. You find out theta. Okay, then theta will have many values, right? Theta will have infinitely many values. It's not a single value, right? If you find theta equal to say pi by 3, I will say theta will be equal to pi by 3 plus 2n pi or any n in
Mr.
the
Firoz,
complex.
please mute your mic. Mr. Firoz, please mute your mic.
So my point
Sourav,
is,
please.
if you say your theta, the theta you find out is pi by 3, then I will say theta is equal to pi by 3 plus 2n pi also. It will give you the same thing. Okay. The point is that you find your theta, all possible thetas, and try to find out which among them lies here. There will be exactly one among them that will lie here. There will be exactly one among them that will lie here. And that is what is the principal argument. Okay.
Sir, I have one question.
Please.
Sir, why the argument for zero complex number is not defined? One thing is that you can write 0 is equal to 0 plus I into 0. So if you try to find tan theta, so it will be 0 by 0, which is not well defined. So this is the one way. Can we think another approach? I mean, geometrical approach.
So that is something, yeah, argument is not defined. This is just definition. Argument is not, we don't define argument for the zero complex number. Okay, we just exclude it. Now, if you say why don't we define? So
Geometrically, it is vacuously true, trivially true.
Yeah, geometrically it is trivially true.
Trivially true.
Yeah.
So,
for example,
yeah,
for
please,
example,
please,
if we define the multiplicative group, as I said yesterday, C minus 0 is a multiplicative group. We don't include 0 because the 0, we cannot define inverse otherwise. Now, if you question that why 0 is not included there is no answer. The point is that we are just excluding 0 just for our convenience. Here also the same thing. We are defining argument for non-zero complex numbers, but the zero complex number, it is trivial anyway.
Sir?
Yeah.
So can you explain some other additional property of the exponential function, sir?
Say that again, please.
Additional properties of an exponential function, sir.
Mm-hmm.
Like suppose take a straight line in C, then how it map from E from straight line to another complex line C. How the transformations like that. That is
He's asking
considered
the
as
mapping properties that if you take a straight line under E power Z, that means the elementary mappings is asking.
No, I did not get the question. So does it?
Can I repeat, Sourav?
Yeah,
so
please.
suppose if you take E power Z is equals to E power X into E power IY. Now, if you take a line parallel to X-axis with 2 pi periodicity, if you take, so where this line is mapping into that one. So this kind of
you were taking a line and you were well, just a second. So here we are writing 1 second. Definitely e to the z is e to the z is e to the x plus iy, and this is e to the x e to the iy. We have seen this.
Take a line
now
L equals to set of all x plus iy such that x equals to 0 and y equals to pi. So the x belongs to R and y equals to say 2 pi R pi. Then she wants where it maps.
X equal to 2 pi.
X is equals to R. That means x belongs to R.
R.
Set of all real numbers. That means a line parallel to x-axis with width, say with height pi.
So that means
yes.
That means
yeah.
You are meaning this line.
Yes.
This line.
Yes.
This height is 1.
Yes. Maybe pi we can take for our convenience.
Oh, whatever. Okay, that's what something one can study. You just verify this. What is the image of this line?
Yeah.
So it's not. You just put it here. Put it here in the definition. Okay. Your y is fixed here. So this is e to the x cos y plus I sin y. So this part is held fixed, right? This portion is held fixed if you fix this line. Now it all depends upon this real exponential. Now you can just plot this and make a graph of this function. You hold this portion fixed and you know the graph of the real exponential, right? You can study this. So it will be that constant times the real exponential, as simple as that.
So any other questions?
Also,
sir,
it's like parallel to y-axis, then how we'll get the transformation, and suppose we take a strip like that or a circular disc.
Yeah, see, if you take that e power z is equals to Sarika madam, so e power z can be written as e power x and e power iy. Take its absolute value, that is same as e power x. Okay. So this will be, yeah, this will be a circle with radius e power x and with argument y. So how much you are taking the argument, you can see that.
Oh, that's what she wanted to mean. Okay.
Yeah.
What you find now? So these things are, these things are very easily determined.
Yeah.
If you just look at the function, the definition, and you put the values of your choices. Okay. If you say you want z from this line, you just put it here. So this part will be held fixed, and you will have the constant times this exponential of x. If this part is 1, then it is just exponential of x. Yeah. And you just plot it in the plane and get the geometry.
Sir,
Yes.
sir, I just want to clear that the principal argument which we define from minus pi to pi. So can you define this like this argument of z, principal argument, that open alpha to any alpha plus 2 pi? In this way, we can define.
This is not principal argument then. Principal argument is fixed, and principal argument when theta lies in between this interval, we call it the principal argument. This is just a name, once again I repeat. This is one of the branches of argument. This is a multivalued function, and this is one of the branches. You get me? When theta lies in between this interval, we call it principal value. Otherwise, if theta lies in some other interval of length 2 pi, okay, that is another branch of argument, but that is not the principal one. The principal one is this thing, and that is a convention just we follow. We call this interval to be principal. Okay.
Thank you, sir.
Yeah, you can choose any other interval, no issue, but we give it a name. When the interval is minus pi and pi, we call it the principal argument. As simple as that.
Yeah.
So if there is no other question, then I seek permission from Professor Allu.
Sourav, you have given a very nice lecture, second lecture. So thank you
very much.
And I'm really happy that participants are really participating in the lectures.